Good afternoon. I apologise in advance. I'm actually a soil physicist, and so I speak another language, and it's not the language of the agronomist or the grower. But if it gets too much, just raise your hand and I'll revert back to something vaguely English. This is the first time that I've had the opportunity to actually present this work that we've been doing for 5.5 years now. And originally it was a GRDC funded project that came under the banner of the Southern Farming Systems suite of projects. And this one was really a fairly pure knowledge-based project. You know, it wasn't sort of an applied project. And after the end of 3 years, we received a further project and a further 3 years funding because we felt that the work that we were doing was quite important and that we needed a little bit longer to actually measure this soil evaporation. So how much water are we losing, and are we getting this right in the models? So there'll be two parts of this. The first part is that I'll be talking to you about how we actually measured soil evaporation, and then the next part is we'll be looking at some of those results and how we use those in the models that we're currently using. So why soil evaporation? Why are we interested? It's the biggest part of the soil-water balance, and we all know, whether we're landscape scientists, whether we're agronomists, whether we're growers, that the soil-water balance is critical for yields, for understanding processes, for understanding landscape health. And it's the biggest term, but it's also one of the hardest to measure, and we have very few actual measurements of soil evaporation in Queensland. There's literally just been virtually no research on it until this project. And the way that we've traditionally measured soil evaporation is we've just derived it from getting measurements of soil water. And then we've just said, okay, this is how much water we have in the soil. We have a bit of a guess at the runoff, or we may have some values for that. We have a bit of a guess at the deep drainage, which is another really tricky one to measure. And we say the difference must be due to soil evaporation or plant transpiration. And often we do a lot of ET studies, but not so many just soil evaporation studies. So the objectives of this project, the last project and this project, really have been to measure soil evaporation on our key soils in the northern growing system. We've wanted to use this data to understand how the soils evaporate, and we want to validate the way in which we're modelling soil evaporation in our models. To do this, we've validated the model in the APSIM and how leaky, basically using the models that we use in research, the models that you would use in decision tools. We've basically done a quick test run of all of those, and I'll show you some of those results today. So we want to get better parameters too to put in our models for our soils and our climates. So currently, what are we using? At the moment, we're still most of our models, and we're using a very old two-stage evaporation model developed by good old Joe Ritchie back in the late 1960s, reported in the early 1970s, and we're still using it. Now, he built that model based on 6 sets of data in the US. Some of those were lab-based studies, and basically we've been adopting that method for the last 40 years for our Australian soils. He uses there are two parameters and a two-stage model, where the first stage is U, and that is a very initial stage after rainfall where there's rapid soil evaporation, which is equivalent to the potential evaporation rate of, say, a free water surface. So that would be the same rate as your pan evaporation, and that runs for a certain number of millimetres. The second part is Kona, and that parameter is really just the slope of the drying curve against the square root of time. So the soils that we chose, we basically went to some of the main research trials that we have been looking at agronomic research over probably the last 20 years as a soils research group, and we selected some of those sites. Some of them you'll be quite familiar with, and we chose those based also on a range of soil textural properties. So we've got a range of clay contents from very sandy soils with a clay of only 12%, going up to very clay-rich soils on the downs with a clay content of nearly 80%. And those sites are at Kingsthorpe, Wallumbilla, Nindi Gully and at Mulga View. So when we went to these sites, we wanted to actually collect cores that we could put into lysimeters. And if you haven't heard of a lysimeter before, it's just a big container that you use to house soil for either measuring evaporation or water fluxes out the bottom, deep drainage. So it's really just a closed system that allows you to monitor change in weight and volume of water. And so we went to these sites, we wet them up for 6 months so that we could make them lovely and moist. We also dug pits, and what we wanted to do was all these models have a set of soil hydraulic parameters that you will be putting in, and we wanted to measure all of those. So we measured our PRWCs, our bulk densities, and we got our water retention curves. So what do we do with lysimetry? Basically, it's like a giant scone cutter. We go out with an excavator and a big team, and we gently push these galvanised steel lysimeters into the ground, dig them out, bring them back, and then we put them into liners in the soil, and they sit on a triangle base of load cells, and what we do is we weigh weight change. So the way we measure soil evaporation is we measure the change in weight every 15 minutes of that volume of soil. And basically, because it is a closed system it's only rain in, soil evaporation out, with a little bit of deep drainage that we monitor from time to time. All those losses that we're measuring every 15 minutes are actually soil evaporation. This is what a lysimeter looks like. Basically, we put suction cups into the bottom of those so that we can apply a suction at the bottom. It's very important to get a lower boundary on a lysimeter so that you don't have water ponding in the base and potentially enhancing your evaporation rates. And we also like to have the image on the right is just the liner that we sit them on in the soil. The whole setup out at the site looks something like this. There is a suction setup, we have climate stations, logger boxes. It's actually quite a big and complex setup. For each of the 4 soils that we sampled, we took 4 replicates. And this is how it looks in the paddock, and this is our lysimeter farm at Kingsthorpe. Lots of you have actually been and seen the farm over the last few years. And you can see quite clearly the 4 different soils, all the logger boxes in the centre, and then what we call a plumber's nightmare on the surface with all that spaghetti pipes of suction and logging and wiring at the surface. We also have a stack of capacitance in there so we can track soil water. On the left-hand side, all those boxes house containers, suction pumps, vacuum pumps, so that we can actually apply a suction to the base of those lysimeters. We also have a rain-out shelter, so that if we want to, we can cover the lysimeter farm if we have really big rains, flooding rains, or if we want to extend a drying curve. If we want to see, what happens when we really severely limit the supply of water in these lysimeters, and, do they keep chugging away, or do they actually stop evaporating? So what we were really careful to do was, when you do any kind of research work where you do lysimetry, you have to avoid the artefacts. Most important is to use undisturbed cores, not to repack your dirt, because you really don't want to disturb the porosity and the hydraulic continuity of those pore spaces in the soil, because that determines your evaporation. You want to use as large as you can and as deep as you can, because bigger is definitely better with lysimeter studies. But it can't be so big that you can't handle it. We had to design a heap of specialised gear just to be able to flip these things over and move them around in the paddock, because they're like handling a little pony. They're about 300 to 400 kilos in weight. The other thing, very important to control the lower boundary. I showed you the suction systems, and because if you don't do that, you're essentially just puddling water in the bottom of a big tin, and then you wonder why you get these really enhanced evaporation rates. And I'm only saying that because a lot of the earlier studies worldwide didn't have a lower boundary, and they measured these really big evaporation rates every day. And we still refer to some of those rates, and of course they're all enhanced and fairly unrealistic. The other thing we did was we put a whole heap of soil around each of the lysimeters so that when it rains, as you know, you get, every time rain falls on the surface, you get splash, and that splash carries small particles of soil. And if soil is continually splashing out during a rain event and no soil is splashing back in, non-interactive, then you wonder why you're losing, a centimetre of soil out of your lysimeters every time it rains. And of course, we have our rainout shelter. So how do our soils evaporate, and how much water are we actually losing? We have, over the period of 4 years, we've had 65 rain events that were greater than 4 millimetres. We've collected over 50 drying curves for each of those soils in that time, and our cumulative evaporation looks something like this. Now, I've reset that cumulative every time it rains. You reset, you start again, and you can see there that's just natural rain. We haven't applied any artificial rain because that also creates all sorts of artefacts in your measurements. And you can see, just as an example, we didn't get that suction system working for the first 6 months, and if you look at that curve between the 1st of May and 1st of July, you'll see the light blue curve at the top, that's Mulga View, and it just raced ahead after a period of time, and that's because it had a whole heap of water in the bottom, and when we applied the suction, we just pumped out litres of water, and of course that water was just going straight up and straight out, and we were measuring it as soil evaporation. But in the real world, that would never occur. It would be deep drainage. So we've got another 3 years, no need to go into that in any detail, it's just to show you that we have all these different drying curves. In the second year, we were very curious to find out how much evaporated when the soil became supply limited, when it really dried out. So we did some very long extended drying curves, and you'll see those in 2011. In 2012, or in 2011 and 12, we also had floods. And unfortunately, everything flooded out there, and load cells that are supposedly water resistant are a bit like a cheap water resistant knockoff watch. You don't want to leave them sitting in water for 4 days and they fail. So we have had to pull them out and reinstall gear. So we've lost a bit of data in those years too. But we also pulled them out for a few months and installed a stack of moisture content sensors. And then last year we thought, every single year we've starved these poor lysimeters of all the potential rainfall they could have because we've used our rainout shelters. Let's keep the rainout shelter off. Let's see how much evaporates just under normal conditions. And except for the January floods of 150 millimetres, which we did have to cover them for because they would have just drowned again, they've had natural rain all year. And we also cultivated the surfaces because we were sort of curious to see if that enhanced the evaporation rates as well. So this is a very big table. All you need to do is, this is a really gross measurement. It's such an enormous data set and it's so complex and there's so many interactions, it's really hard to provide a simple message. But I've attempted to do that by giving you yearly averages for the different soils. Now, yearly averages, if you look over at the right-hand column, you'll see that in 2010 to 2013, our daily average evaporation rate, if you averaged it over the entire year, is steadily increasing. And of course it's increasing because in 2013 we did cultivate and we did get more rain on it. Don't know which one affected it. And there's little differences between the soils. The black vertisol definitely evaporates more than the other soils. The other soils are all fairly consistent. But the black vertisol has a low bulk density, it's very porous. It also has the biggest bucket, so it has the most to lose, and so it does have a higher evaporative rate. And really in these kinds of systems, anything that goes in eventually goes out again too, because it is a closed system. So these are supply limited, meaning rainfall limited systems. They're always running a little dry. So if we had more rain and if they were wetter, you'd probably be looking at more like 1 millimetre a day evaporating in that climate every single day of the year. So, but of the percentage-wise of the amount of water we gave them, they lost about 80%. 80 to 90% of what we gave them, they evaporated. So a huge amount. What goes in just comes straight out the top again. And they're quite deep. They're 80 centimetres deep, but they evaporated all the way through. So, the evaporative zone is quite deep. Definitely there are seasonal effects. If we look at the top graph here, the top table here, you can see that, actually, firstly, what we did was we sort of went, well, we used some linear mixed modelling to start to try and tease out the story of what's actually happening here. And so we broke all these drying curves and rainfall events up into small falls, medium falls and large falls. And you think, well, obviously that's going to affect our evaporation rates. And yes, it does. Large falls, there's more rain, so you lose more. Summer, there's more evaporation. Obviously it's hotter, so you lose more. So everything's quite logical and what you would expect. And those summer losses can be closer to 1.5 millimetres a day fairly soon after rain. Also, just to show you that at that lysimeter farm, we do have 2 lysimeters that are just water-filled and they measure our pan evaporation. And just to give you an idea of what the annual pan evaporation is for those climates, in the little table down below, and it's 6.5 millimetres a day in summer on average and only 3 millimetres in winter on average, so about half in winter. And I just wanted to show you just a little bit about what actually happens when it rains and what happens to that water and how do we lose it to evaporation. So I've got 2 of those drying curves. I've just shown you, I'll just show you this one first. It's just after a small fall, 6 millimetres of rain. And if you're already a grower, you know that you lose that 6 millimetres very quickly. And yes, we measure exactly the same response. So the top blur of lines, they're just the 4 soils averaged, the reps averaged, and the bottom line is your water, your pan evaporation. And it shows you, the potential evaporation rate each day. In the first 24 hours, we lost 3 millimetres, so there was a good little loss there. But the pan evaporation was 5.2 millimetres. It was considerably higher. Within 2 days, all of that 6 millimetres had evaporated. If you look at the top line, and you'll see that it just goes back to the same old position after 4 days. So those small falls, and we find this again and again, small falls, then they're gone. And this was an autumn drying curve, so it wasn't excessively hot. All right, so now let's have a look at a really big rainfall. When you get a really big rainfall event, there's 50 millimetres have fallen here on these 4 soil types. And that 50 millimetres fell over about, I can't remember exactly, about a 14-hour period, I think. And we find in the first 24 hours, the average soil loss was 4.7 millimetres a day. That was the average in the first 24 hours. And then it slowed down. The potential evaporation was 6.5. And I'm making this point because those of you who don't model and don't use Ritchie's U and Kona parameters will be going, possibly it should be a little bit higher than that. But anyway, so we do lose a considerable amount, and you can have each one of those squares is a 2-day time slot, and you can see how quickly you're going to lose 20 millimetres in the first 2, 4, 6, 8, probably 8, 10 days. So quite a lot of loss. But this is summer, and it is hot. This is a big summer storm, hot, humid conditions, but really rapid losses off bare soil. So let's have a little bit of a talk about U and Kona. Hopefully a lot of you are modellers, so you'll know what U and Kona are and what they're all about and why we're curious. And the reason why we're curious is because nearly all the models you use, APSIM, how wet, how often, yield profit, all those models have parameters of U and Kona in them that predict the soil evaporation. And it doesn't matter whether it's bare soil or covered soil. This is the starting point for a model. It will just adjust that for a covered soil. So U, as we've said, is the amount of cumulative evaporation before the soil supply decreases below the potential evaporation, the atmospheric demand. And basically for all of these curves, we've got nearly 200 drying curves across these 4 soils. It is a massive data set worldwide. Joe Ritchie would have probably been given his right arm for this data set 40 years ago. But we find for all but 5 of those, after the first 24 hours, we had lost between 0.1 and 3 millimetres of rain, and that's it. It's not a massive amount. So there is a bit of a furphy out there that U is a very high number, and U is not linked to time, But certainly, you are assuming for a period of time after rain that soil will evaporate at the same rate as a pure body of water. So there's got to be some free water, and after 12 or 14 hours, that water is absorbed, or after one day of good sun, that water is absorbed, and it's definitely slowing down. So after 48 hours, all except for the really 5 big curves had only lost between 0.4 and 6 millimetres, and definitely you should be over by then if you look at the process of evaporation on a soil surface. So we would recommend that you actually be quite a small number. If you're looking across these 200 curves, you would find most of them would be less than 2. Kona. We've also calculated, we calculated a set of konas based on each drying curve, and we just took the slope of the cumulative rate of drying to time to the half. And these are the values that we've come up with for 4 different soils. What we find is that for 3 of those soils, with really contrasting soil textures, by the way, there's no difference. The konas of around 4.6, 4.8 are just perfect. They're absolutely fine. The Kingsthorpe soil definitely needs a higher kona value. And of course, summer, spring and autumn, no difference between those seasons, but winter, you definitely need a much lower value of around 3 for these soils anyway in this climate. So lots of people over the years have, in their attempt to find the perfect kona, have wanted to look at potential evaporation and link it to kona. And there's good evidence to see why you should do that, because potential evaporation is an indication of the evaporative potential in that environment, and why wouldn't kona link with it? We find it's actually, in reality, there's 200 points there, it's pretty messy. Some of those sometimes we get really high potential evaporation in summer, but the soil's dry, so it couldn't evaporate if it wanted to, so you get very low konas for those drying curves. Sometimes nice wet soil, nice moderate and middle of the year kind of conditions, it just chugs away, you lose a massive amount. So it really is very strongly linked with how much water is there in your soil to evaporate, and if there is water, you will lose it. So are we getting it right in the models? And these are the models that we use for all of our agronomic processes. First of all, the CSIRO guys who are on this team, Jeremy, Neil and Justin, they did some initial modelling where they used APSIM, and APSIM uses 2 soil water balance models, SoilWat, which is also used in how leaky and sort of in how wet, and the SWIM model, which is an advection, dispersion, and Ritchie's equation model. It's a physical-based model. So they used both of these, and they took all of these drying curves and they put them into those models, and they said, well, how well do the models model the measured data? How often do we do that, Fairly rarely, at least with 200 data points. Okay, so basically what they found was, on the left-hand side, this is the modelling with how what, and it probably looks a little messy to you, but actually we're all pretty happy with it. The model does tend to predict, we used our empirically derived U and kona values in this model, by the way. The model does tend to follow the pattern very well of our empirical values, which means our empirically derived values are accurate. The actual way the model works to predict soil evaporation seems quite okay too. However, it does underpredict. All the modelling that we've done pretty much underpredicts soil evaporation. The SWIM model also does a good job, but it has a lot of trouble coping with soils where you have rapid increases of water in the saturated zone, and so we couldn't model the Mulgaview soil at all after rainfalls, because they sort of go from very dry to very wet very rapidly, and then very dry again, all within 6 hours. And it was just too much for that model. So we thought, okay, we've shown from this APSIM modelling that our U and kona values are good, that the actual structural basis with which we model soil evaporation, APSIM's doing a pretty good job of it in both the SoilWat and the SWIM components of the soil water balance. So then we had a look at how leaky. This is just, don't look at those numbers, we just parameterised the how leaky model and the APSIM model with our measured soil parameters. Then what we've done is, this is a how leaky model looking from 2010 to 2013. We just modelled 4 years of measured data. And we used a couple of different U's and Konas. We used the APSIM standard. We also used a seasonal APSIM because you have the capacity in APSIM to put seasonal values in, and that usually improves things. And we looked at our measured, and I think over 3 years looking at that, the measured is the green one, so basically you want your model to match your measured, and I think it did a pretty good job over 3 years on this black vertisol. It was only 50 millimetres under predicted, which per year is a fairly small amount. It gets even better. Just look at that yellow, keep your eye on the yellow dot, because I'm just going to run through the soils. Looking at the Nindi Gully Grey vertisol, 20 millimetres difference in 3 years. So I'd say that is a fantastic outcome. You know, it's saying this model is capable of predicting soil evaporation really well. And that's using either our values or the APSIM standards. Wallumbilla, same story. However, when we get to the Mulgaview soil, we had a complete failure. And the APSIM standards didn't model that soil at all well. So obviously probably need some better U and Kona values in APSIM for that particular soil. Didn't do a bad job of modelling our empirical, but it definitely in periods of waterlogging before we got that lysimeter up and running. In fact, this is a case where a model tells us our measured data is wrong, and I love it when that happens. So back here where you see the waterlogging, that's before we had the lysimeter. We had the suction in, and, you know, the Mulgaview just filled up with water, and it's just going, shh, you know, like it's just pumping away, and we get these really big evaporation rates, and you can see it right there, because once we've got the suction working, everything comes back into line. So what are the effects on predicted crop yields? This is probably the bit that will interest a number of you who are doing agronomic modelling. We used APSIM, and what we did was we wanted to just test it for 2 crops. So we looked at wheat, we looked at sorghum, and what we wanted to do was we wanted to look at the effect of modelling the fallow before cropping either of these crops, and modelling stored water, how much water we're storing from harvest to the following planting, and how the models are predicting that, and if they're doing a good job of predicting that. So to set our harvest soil water, we just ran the model for 50 years, took the average, which was about 9% of POWC. And we wanted to look at the effects both on soil water and on subsequent yield. For wheat, it's a summer fallow, so obviously that's when you're going to get your big evaporation rate, so this was the one that we were really interested in. And what we found was the difference between the way the model did it and the way our measured data does it is that we had an increase in fallow evaporation using our actual empirically derived parameters as opposed to the generic APSIM ones. There was an increase in fallow evaporation, leading to a lower soil water at planting, leading to decreased yield. In other words, the model underpredicted how much soil water we lost to evaporation during the fallow. And these are the 4 soils. It's a little bit messy, I know, but basically you're looking at the difference in soil water deficit between using our measured data parameters and the APSIM generic ones, and what we're finding here in every single case is that, on the y-axis, that is your yield difference. Okay, so we're looking at over 50, we modelled this for 50 years, over 50 years, for Kingsthorpe, you're going to have a 370 kilo per hectare difference in your yields, i.e. they'll be lower in the real world than the model's telling you they should be. And it varies. Some years almost no difference, other years a lot of difference to almost a failed crop. And that's because it is under-predicting how much water we're losing. And so it's leading us into thinking that there is more stored water than there actually is in the system come planting. Mulgaview, quite a lot. Nindi Gully and Wallumbilla not so much in terms of yield differences. When we looked at the sorghum has a winter fallow and therefore it's got lower evaporation rates, and we were expecting to see a slightly different story. But what we got a completely different story, and our soil water deficit varied widely and completely inconsistently using APSIM standard and our empirically derived U and Kona values. So we either got higher or lower soil water at planting, we got variations in timing of growth stages, variations in harvest dates, and increases and decreases in yield, as you can see here. So anything below that, anything below zero means that APSIM did a better job, and anything above means that the empirically derived values did a better job. The next thing we'll do is we'll run this through with some actual yield data, if we can get a good data set, and test it out there. So how do we expand the usefulness of this data set? Basically, you can use multi-dimensional machine learning algorithms to start pouring through this massive data set and find the patterns that we can't immediately see. And that is something that if we have the time and resources, we would definitely like to pursue, because there's a lot more information. Having a data set this big, basically you could be writing papers off this data set for the next 5 years, you know. How have we applied it? I was talking to Dave Freebane. He asked for these U and Kona values, our new U and Kona values, to put into Climate, into how wet. And I said, well, how long before you're going to have that in? And he says, tap, 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 I'm typing them in right now. So that was an almost instant application of our data set. Dave McClimart, who is looking after how leaky, is going to incorporate some seasonal U and Konas, because it definitely improves our prediction of soil evaporation for certain soils. And for the last 2 years, as part of our Lockyer Valley agronomic modelling, we've been using our new parameters, and it will continue to bud out. I hope that people all over the place will be using better parameters in their modelling. And last but certainly not least, this research site has been a tremendous bonus for us as a research team, for the other research teams that we work with. We've been able to take international visitors, collaborators, dignitaries, all sorts of people out to have a look at this research. And over the years that we've been taking people out there, you know, we have a couple of standouts. We actually got the Director General, who has the very city boy hat up in the top left there. He actually came out 6 weeks ago. It's the first Director General from our department who's ever taken the time out of his busy schedule in Brisbane with the pollies to actually come and spend a morning with us at our research site. Late last year we had the fellows standing beside the GRDC sign. We had the Honourable Major General Michael Jeffries came out, National Soil Advocate, and he highly praised this research and felt that it would be very important to do more of this for the soils around Australia. So, and you'll recognise yourselves, a few of you, in these shots, but it has been a wonderful facility for showcasing research in southeast Queensland and showcasing what GRDC, you know, is capable of investing in. Thank you. I think the parameters that we've come up with are spot on for the way in which we're modelling soil evaporation using the Ritchie model. But quite possibly the Ritchie model is not perfect. But look, for a lot of the soils it still does a good job. But in a lot of cases, we are assuming using the Ritchie model that soil is losing water at a rate equivalent to an exponential decay function, time to the half. And in fact, it's a little more linear than that. And that's probably why the model tends to underpredict evaporation, you know, in the longer term. What we tend to find is over time, you know, lots of short, sharp rainfall events, yes, you'll really see those differences in either having cover or in having, you know, a more bigger macroporosity, you know. But over time, they do all equalise out. Once the water's lost, it's lost. You know, and if you have a 20 millimetre fall in 3 weeks, regardless of the systems, you're going to have lost it all by the end of that, if you know what I mean. So yes, they're all the sort of subtle soil physical aspects that you do need to consider, and it's certainly one we think about, but there's not much we can do about it for this bit of research. In lysimeters, you get a lovely crusty cracking surface, but we just never saw those deep cracks develop because there were not it was an even soil hydraulic gradient and soil water content throughout that soil. There was no differential to create cracks, and cracks are caused by hydraulic differentials. So in cracking, this was something we actually talked about recently. How much extra water do you lose in real systems where there are big cracks? And I really don't have a ready answer for you there, except to say you and I both speculated it could be considerably higher. Basically, your open water surfaces are evaporating at that higher rate, and we had the figures of 6.5 and 3 for certainly that southeastern climate, summer and winter, and that's your average daily. So you lose a lot of water from an open water surface, but not so much from soil. So, if your water is in your soil, you will lose less. I see what you're saying. Should we pop it in the soil as a storage mechanism? It's a very interesting concept, and it's something that probably you'd want to sit down for about an hour and think about and do the maths on.